In this lecture, we are going to learn a new idea called power series. Power series. So, as the name tells, you may see that it's a series, but you're going to see powers of a certain unknown. So, let's write the definition. A power series is a series of the form this is how we write it, sigma. We normally start with n equals 0, but you can start any other numbers also. Cn xn. So you can see that. So you see a number Cn, and then you have x to the power n. So that's how we call it a power series. It's a series but with powers. So if you expand it, you're going to get C naught. Why we get C naught? Because the first term is C naught x to the 0. By convention, we assume that x to the 0 is 1. So that's why we kind of ignore that term. Even in x equals 0 case, we just write it like that. It's just a notation. So, and then we have C1x and then C2x squared, like that. So in general, you're going to see Cn xn. So that's how it looks like. So I'm going to call it this equation number 1. So this is how a power series looks like. And then where x is a variable, and Cn's are called coefficients, So that's how it looks like. So and then you can see that for each x, for each fixed x, so then x is just a number after that. If you fix x, it's just a number. Once you plug in it, you just get like a bunch of terms and you add them. So it's just a regular series, right? Just a regular series. So for fixed x, sigma n going from 0 to infinity, Cn xn is a series. So as we learned before, it's a series that can converge or diverge. That can converge or diverge. Right? And the nth term has the form an equal Cn xn. So you can see that that's just the nth term, and Cn is maybe some expressions of n. X is just a number, so this is just a number, right? So you are just adding numbers. So which is a number? Okay. And then we also see that the sum of the series, if you sum it, all of them with x in there, it just becomes a function. It's a kind of weird function because there are infinite many terms, or it's a polynomial actually. But with it's not really a polynomial because polynomial has to stop at some point. So this is not a polynomial, it's a polynomial like. This is not a polynomial. Polynomial has to stop at some point. So sum of the series is a function. Sum of the series is a function. So we can write this as fx. This is just a c0, c1x, c2x squared, like that. But you can see that this never ends. It's a series. So if you write the general term, it looks like that. So we can say looks like, okay, looks like a polynomial, but it's not a polynomial. Looks like a polynomial. It's not a polynomial. Polynomial has to stop at a certain degree. Okay, so this is not a polynomial, but has infinitely many terms. Infinitely many terms, because we know that if you have a polynomial which has a degree, so we say degree 3 polynomial, degree 4 polynomial, so this is not a polynomial because the degree is infinite, so it's not a polynomial. So let's look at, like, some special cases how it looks like. So that, so any expression we write it like this has a can be like a we say a power series. Okay, power series. So let's look at few examples just to get the kind of idea. So let's set some numbers. So example, so if you set Cn equal 1, what will happen if you split Cn equal 1? You're going to get n going from 0 to infinity, xn, because Cn equal 1. So we expand it, you get 1 plus x squared plus x cube. So this is just geometric series, right? So geometric series. So geometric series. In this case, R is simply x, and then we know that converges when the absolute value of R, in this case absolute value of x, less than 1. So that means the interval from -1 to so you can see that this is simply -1 to 1, right? So that's the interval. So on this interval, this one gonna converge. So we discussed this a lot of time. 1, -1, that's where it's gonna converge, and the outside is gonna diverge. Good. So converge here, and the diverges when x is greater than or equal to 1. Good. So let's look at more example. How about if Cn equals 1 and x equal -1/3? So then the series looks like, the power series looks like it going from 0 to infinity, -1/3 to the n. If you look at few terms, so the first term is 1 minus 1/3 plus 1/9 minus 1/27, like that. So, and then in this case R is -1/3. This implies that the absolute value is R is 1/3, so which is less than 1, so converge. So this series converge. Again, converge on what? So you can see is converge from -1/3 to +1/3. So right, so -1/3, +1/3 to -1/3. Inside this is going to converge. Okay, good. And then if, let's say, Cn equal 1 and x equal 3, what will happen now? So it's going from the 0 to infinity, 3 to the n. So you can see that 1 plus 3 plus 9 plus, like that, diverge. So anything can happen, So there are intervals where it's going to converge, and also there are cases where it's never going to converge. So for example, the last one never converge. Good. So in this case, it's not really useful. So let's kind of consider what can happen in general. So we're gonna write this like this. So in general, a series of the form sigma n going from 0 to infinity c, and we're gonna make it a little bit more sophisticated. We're gonna say x minus a to the n. So you write it like that. So if you expand it using the same convention, first one is c0, second one is c1 x minus a. So we already write c naught. That's the kind of convention. And then c2 x minus a squared, like that. So that's the form. So I'm going to call this star. So this is the general form we're going to consider. So you can see how it looks like. We have a number and the power x minus a to the power. So it's called a power series. It's called a power series. It's called a power series. In x minus a. So that's the term. Power series in x minus a. Or there are three names. Or we also say power series. We say power series centered at a. Centered at a. That's another one. Or we say power series about a. Power series about a. So those are three names. So just pick one of them. Different people say different names. So one is power series in x minus a. That's the least common one. And then we say power series centered at a, or we say power series about a. So there are three ways to say it. Anything works. So let's look at a small naught. So naught when, let's put x equal a in there. If you put x equal a, what will happen to the series? If x equal a, you can see that except the first term, all the other terms become 0. Okay, when x equal a, the star becomes so what will happen? Sigma n going from 0 to infinity, c n x minus a to the n equal c naught plus everything else is 0. So that means c naught, that means always converge. Converge means you get a finite number. That's what converge means. So it converge. So it converges always. It converges always. So that means at x equal a, it converges. At x equal a, it converges no matter what. And then there's an interesting thing. So now the question is, when a general series is going to converge, where are the general series going to converge? Whether it's going to converge at a point, when it converge as an interval, or everywhere. Actually, there's a result. It says that there are only three possibilities. So there are only three. There are only three possibilities. There are only three possibilities. So let's put them in a theorem. So this is the most important theorem in power series actually. So so let's look at that. So we're gonna consider this as a theorem. So three possibilities. Okay, so it says that for a given power series, okay, for a given power series, for a given power series, for a given power series, sigma n going from 0 to infinity, c n x minus a n, only one of the following happen. Okay, only one of the following happen. So there are three cases, but only one works. So what's the first case? Series converge only at x equal a. Series converges only at x equal a. The second one, series converge everywhere. Series converges for all x. For all x. That's the second case. It's converge everywhere. The first one is only at a. Only at a. Only at a. So a is that number you're going to see there. So only at a. The second answer is converge everywhere. The third case is really interesting. There is a positive R. There is a positive R such that two things, such that a series converges in x minus a less than R, B diverges in x minus a greater than R. Now there's a question. So what's going to happen in the corners? Because there's something missing here. What happened x equal a? What happened? Because we say less than or greater than. What happened equal? So when it equal, you're going to get two numbers. For those two, we have to check what's going to happen at those corners. So let's write it. First, we can write some few more things. This R is called the radius of convergence. Radius of convergence. And then we can say all x such that the series converge, all x such that the series converges, all x such that the series converges is called the interval of convergence, interval of convergence, which has four forms, so it can be because R is the radius of convergence, so you go R away from A, but there are four ways. So what are the four ways? So it can be A minus R, A plus R, or one of the corner can be closed, so it's A minus R closed and then A plus R open, or A minus R open, A plus R closed, or the both corners are closed, A minus R, A plus R, A minus R, and then A plus R. So the question is, what do you do with the corners? So what you want to do, you want to consider the endpoint separately. Okay, that's very important. So consider end points. There are two endpoints separately, because we cannot say anything about that. So sometimes we can use those P series and alternate series test for that. So use P series or alternate series test or any other test, okay, or other. So these are the common things. We use P series and the alternate series test to check the corners. So let's see what's going to happen in a few examples. So the first one, and then also one of the major thing that we do is we use the ratio test here. So we use the ratio test to find R. We use the ratio test to find R. So let's look at some examples. So let's do like about 3 or 4 examples. So for what values of x? For what values of x? does the following series converge? Does the following series converge? Find the radius of convergence and the interval of convergence. So let's find the radius of convergence and the interval of convergence. So the first example, let's look at this one. So this is like very common problem, n going from 0 to infinity, factorial n x to the n, factorial n x to the n. So if you get a problem like that, we just proceed as we normally do. So like we're gonna pick a n, so it is xn factorial n xn, and then a n plus 1, which is factorial n plus 1 x to the n plus 1, and then what you do, you take the limit of the ratio. So right, that's how we normally do. We take the limit of the ratio. So a n plus 1 or a n absolute value. This is important. The absolute is really important in this case. You can see. So it's the limit. Now we're going to plug in. So if you plug in, what are you going to get? The absolute value n plus 1 factorial x to the n plus 1, and then divided by factorial n x to the n. And once you do that, then there will be a lot of cancellation going on. So you can see, for example, xn cancels with this xn, so we cancel n. And then what we normally do is we're gonna write the factorial in a, remember we did like we expand this in a kind of nice way. So limit n goes to infinity, we're gonna write this one as, we're gonna expand this as n plus 1. We pull one term out and leave the rest. In the bottom we have that, and then this absolute value, because we don't know x is positive or negative, so you have to leave the absolute value in there. So it simplifies like this. Now you can see that this get cancels with that. So you simply get n plus 1 square. So you're going to get the limit n goes to infinity, n plus 1 times x. X is just a constant. But what's going to happen? We know that this term goes to infinity, because it goes to infinity. So so that means this limit is simply infinite. No matter what value you pick, is always infinite for any x not equal to 0. So that means if x not equal to 0, this goes to infinity. So due to the ratio test, the series diverge. So that means it's going to converge only at x equals 0. So so we can say the series diverge. So let's say the series diverge. Series diverge for any x not equal to 0, and then and then you can say converges. So this is due to the ratio test. Okay, so and converges you can say converges only at x equals 0. So that's only one value this can converge. So that means, what's the radius of convergence? So you're gonna see that you see that 0 here, but you cannot go anywhere. Right? So there's no r. So r is simply 0. So in this case, r is simply 0. So the radius of convergence equal 0, and the interval of convergence, there's no interval here, it is just the 0 set. So we're going to write this as a set, but there's only one element in there, so it is just 0. Okay, so that's the first case. So you see that there's only one point that's going to converge. The radius of convergence is 0. So sometimes we write this as r equals 0 and ic equal so we write it like that sometimes. Okay, so that's the first one. So you can see there's only one point that is gonna converge. So let's look at another example. How about b? Let's consider this one. So let's look at a little advanced one. Sigma n going from, let's say, 1 to infinity, 1 to infinity x minus 2 to the n over n. How about that? So in this case, a n equal x minus 2 to the n over n. So we can write the as before, we can use the ratio test. So we can say limit n goes to infinity a n plus 1 over a n. So this is the limit n goes to infinity x minus 2 to the n plus 1 over n plus 1 times, it's a ratio, it's upside down, x minus 2 to the n. Remember, take the absolute value sign because we don't know the positive or negative. And then there are a lot of simplification going on as before. This term get cancels with that, so you only get one term. So that means you end up getting limit n goes to infinity. You're gonna get n over n plus 1, which is positive, so I pull out, and then we leave x minus 2 absolute value there because we don't know whether it's positive or negative. Okay, now what happened? We know that this part, the limit of this one is 1, so that means you simply end up getting x minus 2 in this case. But we know that, so that's the limit, but then by the ratio test, now by the ratio test, what happened? We know that if this limit less than 1, it's going to converge. Okay, now by the ratio test, the series converge if this limit means x minus 2 less than 1. So right, so this implies that the radius of convergence is 1. See the 1 here. And then also this is going to give us a interval. What's the interval? You have to go 1 away from 2. So that means we have 2 here, so you need to go 1 away from that, both directions. So that means it's going to be 3 and 1. So that means what we need to do is we need to consider those two corners separately. So we're going to consider the two endpoints separately. So let's see what's going to happen now. So let's say if x equal 3, let's plug in. We're going to plug in that value to the original series. So we're going to get, if you plug in 3 here, so if you plug in 3 here, so it's n over n. So if you plug in 3 for x, what do you get? You get sigma n going from 1 to infinity. If you plug in 3 for x, so you get 1 to infinity is 1, so you get 1 over n. So this is this diverges. Okay, so diverging p series because p equal 1. So that means x equal 3 is not a good point because at that point series diverge. Now let's do the other one also. If x equal the other corner, what's the other corner? 1. So if you put that, you're going to get 1 to infinity x minus 2 over n to the n. So if you plug in x equal 1 now, you're going to get sigma n going from 1 to infinity negative 1 to the n to the 1 over n. What is this? So this, you can see that this is the harmonic alternating harmonic series, but we know that this is going to converges by the alternating series test. It's very easy to see because the bn, that means 1 over n is the bn, that goes to 0 and the limit is 0 and is decreasing. So by the converges by the alternating series test, that means at x equal 1 it's going to converge. So that means the interval of convergence is interval of convergence is, you have to include 1, you have to exclude 3. So that's the interval of convergence, and the radius of convergence is 1. So yeah, so that's the whole problem. You can see that it's not that difficult. but you need to know certain things and how it works. Okay, the alternate series test is important for these kind of problems. Okay, so let's try to do maybe 2 more problems. So let's do another one. So we did the first one converges only at 0. Second one converges in an interval. So let's see one more and see what's gonna happen. So this is the third one. So let's see sigma n going from 0 to infinity n minus 1 to the n divided by factorial n. So in this case a n is x minus a to the n over factorial n. So you are dividing by factorial, but n start with 0. So you see that what is the factorial n, which is n minus 1, like that. So 3, 2, 1, but factorial 0 is considered as 1. So that means you can divide by factorial 0 but not by 0. Okay, so factorial is 1. That's a convention. You can prove that it should be 1 by certain arguments. Okay, so as before, so let's take the limit. N goes to infinity, a n plus 1 over a n, absolute value. So this is the limit. N goes to infinity. So let's plug in here. So it is x minus 1 to the n plus 1, n plus 1 factorial, n factorial, and then x minus 1 to the n. So we're going to simplify as before. Once you simplify as before, n plus 1, the factorial and factorial get cancelled, and x to the n get cancelled. So you simply end up getting limit n goes to infinity. You can see you're going to end up getting x1 of x minus 1 divided by n plus 1. That's what you end up getting. Now there's something interesting here, because you know that x is a fixed number. So x is a fixed number, n goes to infinity, so you're dividing by a large number. That means for any x, this is going to be 0, because you're dividing. X is a fixed number. That's why this is going to work. X is a fixed number, and then n goes to infinity, so this is 0, but this is less than 1 for all x. For all x. So that's very interesting. For all x. So that means you can see converges for all x. Converges for all x. Implies, what does that mean? X can be anything. So that means R has to be infinity. Okay, and the interval of convergence is what? Any. That means negative infinity to positive infinity. So it's a kind of interesting example. See, the R is infinity and it converges everywhere pretty much. Okay, it converges everywhere. So everything. So it's going from negative infinity to positive infinity. Okay, just pick a number. That's your 1. So R is infinity. So you got infinite distance for both sides. Good. So let's do one last problem. So this is the last problem of this section. So I'm going to call it D. So how about this one? So let's say sigma n going from 0 to infinity n x plus 3 to the n over 2 to the n plus 1, something like that. Okay, so as before, and now no changes. N is n x plus 3 to the n over 2 to the n plus 1. So we're gonna take, so I'm gonna do this in a slightly different way. We're gonna only look at the ratio. So n plus 1 over n absolute value. So let's plug in here. So this is gonna be n plus 1 x plus 3 to the n plus 1 over 2 to the n plus 2, and then we can make it upside down. We write it like that: n x plus 3 to the n. So we have that. Now you can see that a lot of terms get cancelled, so you only end up getting one half. So you're gonna get 1/2, and then n plus 1 over n, and also you're gonna get 1 of x plus 3. So you can see that when n goes to infinity, this one goes to 1, right? So that means when n goes to infinity, this thing goes to x plus 3 absolute value divided by 2 as n goes to infinity. Okay, so that's gonna be the limit. Okay, that's the limit. So again, by the ratio test. So then by the ratio test, as before, the series converge if that limit x plus 3 absolute value over 2 less than 1. Okay, now what we can do, we can solve for x. So that means, so what is the r here? We still r, you have to multiply by this. So what we do, we can write this one as so let's write it on so x plus 3 over 2 less than 1. That means x plus 3, if you multiply by 2 both sides, you're gonna get that. So that means r equal 2. So you always need to solve for that first. Okay, so r equal 2, and then this is also going to give you an interval. So the interval is starting at -3, you're going to go 2 sides, 2 distance. That means a -1 and -5. So those are the corners. So what we're going to do, we can evaluate at those 2 corners. Good. So at x equal -1, we're going to get the series n going from 0 to infinity n. So when you plug in x equal -1, you're going to get what do you get? You plug in -1 in the original series. So let's go back to the series. So if you plug in -1, you get 2, right? You get 2. So you get 2 to the n over 2 to the n plus 1. This simplifies very well. This is going to be n over 2. It's clear that this can diverge. Okay, the term just goes to infinity, so diverges. And then at x equal the other corner, -5, sigma n going from 0 to infinity, we have n -2 to the n over 2 to the n plus 1. We can simplify this a little bit. So this is sigma n going from 0 to infinity. You can pull the -n out, and then we have n, and then we have 2 to the n, we have 2 to the n plus 1. So you can see 2n get cancelled, you only get 1/2. It's always a good idea to take it out. So it's -1 to the n. To the n, you can see it's again gonna fluctuate, so it's gonna, numbers gonna go like that, so diverge. So this one also diverges. Okay. So that means the interval of convergence is simply only the original one, so it's a -5 to -1 open interval, and the radius of convergence is 2. Okay, so you can see these problems are not that difficult, but there are some algebra that going on, and then we use the ratio test and the alternating series test and the p series test most of the time. Okay, so we use we used ratio test, and then the p series, and the alternating series test for most of the problems. Okay, so this is the end of power series.